a paper with this title in the Journal of the British Interplanetary Society 20 years ago, volume 44, 1991. And most of the technical details of the math are contained in that paper. I've just picked off a few graphs and things to try to make the point. But I decided before I even began to give you the punchline now, because I'm going to try to make the case for several technical things and hardware things, and I don't want it to be lost. Why am I talking about all of this? Basically, we worry a lot about the technological difficulties of interstellar travel. It's very, very hard to do, and we all realize that. One thing that would be nice is if we could travel at the speed of light. And since I published this paper 20 years ago, quite a lot of progress has been made in a lot of ways, including deciphering the human genome. And I mentioned in the original paper that I thought that would be done sometime. And so, in principle, we can now transmit the human genome to a receiver around another star, planet around another star. And in addition to that, when you really think about it, that's not sufficient, because in order to do anything with that information, you have to have a wonderful little machine that knows how to turn a genome into a human being. And that means a living cell. Now, you can transmit the genome with about 10 to the 12 bytes, which you can do pretty fast with a laser. But if you want to also transmit the recipe for making a human cell, to read that and eventually to create a clone of yourself on another planet, then you're going to need 10 to the 16th or 10 to the 18th bytes. But the point is, it's doable, it can be done. And therefore, if you can find a collaborator somewhere else who receives the signal and knows what to do, then in principle, you can preserve yourself, transmit yourself, and step out and become friends elsewhere. Okay. Now, there are several other things I want to talk about implicitly. I'm speaking about the advantages of lasers over microwaves, and a lot of people thought that was poppycock originally, but it isn't, for very good reasons you'll, I hope, understand. I want to look at it two different ways. First, in the context of the ability to find serendipitous evidence of other civilizations without communicating with them. And then secondly, what I've just been talking about, to communicate. Okay. We have the happy coincidence of having a really nice triple star system as our nearest neighbor, and in particular the double star Alpha Centauri A and B are widely separated. It turns out that about 50% of all stars are double or multiple stars, and a fat percentage of them do have this wide separation. The larger star is 1.1 solar mass G2 star, and the orbiting star is a K star 0.9 solar mass. So they're nicely spaced on either side of the mass of the sun. The periastron distance is about the same as the distance from the sun to Saturn, and the apastron distance is about the distance between Uranus and Neptune. So these two stars have been revolving around each other for over 5 billion years. The system is close to 1 billion years older than our solar system. And Proxima is out there somewhere and co-traveling, but you don't need to worry about that very much. We do observe that system obliquely, and so the way we see the actual ellipse is like this, and I particularly want to focus on that for a minute. Some very nice studies of the stability of planets in such double systems have been done, several of them, in fact, if you go to the web. And this one I particularly like by a group at the University of Toronto. They've done simulations of stable orbits around both of the two stars, and each dot you can consider a proven stable distance from the star. The life zone, as we call it, would be very small right in here. And that's why, actually, we haven't got the proof yet of Earth-like planets around either one of them. It's going to be forthcoming in a few years, I'm sure. But it's a little bit difficult just because it's pretty close in. Now, what I want you to note in particular is that as this star orbits around and comes up here, now it's right along in here, the two become more or less superimposed. So if the Earth is here and you're looking across there, then you see the two more or less in the same direction. If in this extra billion years they evolved technological civilizations, the first thing they would have done is settled their own system with life forms on both planets, and they presumably want to keep communicating with each other if they aren't at war with each other. And therefore, if we happen to be more or less lined up, we're in an optimal position to receive the communication, whether it's radio or laser. Now, think about the Kepler mission, which is now moving along, looking at thousands and thousands of stars. What it is designed to do is to find stars where you're in the plane of the orbit. You can see the star occulting, the planet occulting the star. And this is a perfect setup, of course, for doing the same thing here. When you know that a planet is occulting the star, well then that's the situation where there's a lineup between yourself and the star and the planet, and you can go on from there looking at double systems. There's already a few Kepler systems that are double and so on. Okay, now I'm shifting gears. I want to talk about why lasers are better than microwaves. The traditional assumption that caused all of SETI to be created around the microwave window is that microwaves always win because they contain more photons per unit energy, so the effective photon noise per unit time interval is lower. And that's fine as far as it goes, but that's really not the way you build a communication system. The point is that microwaves are subject to inverse square laws because it takes an enormous microwave antenna to create a narrow enough beam so that you're looking only at the life zone around the star. The wavelength is 100,000 to 1,000,000 times shorter, and therefore the size, the diameter of the antenna has to be 100,000 to 1,000,000 times bigger, and this is an inconvenience. If you design an intelligent system, you don't want it to be photon limited, and we might pick out of the air a nice signal to noise of 100 to 1, which will give you very good quality communication. Much shorter laser wavelengths then permit reasonably small optical apertures to focus the radiation on the life zone of the target star. And that easily overcomes the star noise coming from the sun. Say we're transmitting to a star there, the sun is in the beam, and you're worried about pointing stability and so on. Well, this is great because you have a star there and you can use that to stabilize your adaptive optics, so you know that the beam is perfectly reciprocal, and it will always stay focused right where you want it. This also, of course, minimizes wasted energy because you're broadcasting only to the life zone around the star, not spilling over and seeing vast amounts of empty space. Therefore, the bottom line there is that much higher signal to noise is readily achieved. This famous diffraction equation was shown earlier, I believe, by you, Greg, and basically what it says is that from an optical aperture, when there are no errors in the telescope itself, the beam spread, the angle of spreading, is 2.44 times the wavelength over the diameter of the transmitter. If we can take that, and now we've created a graph here where we're looking at the optics diameter to produce the 21 light minute diameter spot. The Earth is 8 light minutes from the sun. The Earth's orbit is 16 light minutes in diameter. Mars is about 20. That's the life zone around the sun. So for a solar type star, you want to illuminate a spot 21 light minutes in diameter. And look at the diameter of the optics in meters, how far away you can do that. If you have a 10-meter diameter optic, the same as the two Keck telescopes in Hawaii, then you can illuminate nothing but the light zone out to a range of about 200 light years. If you go to a 100-meter diameter, you can go to 2,000 light years out and so on. So it's quite remarkable. And remember, it is reciprocal too, and so when they look back our way, they have a channel. Why do we no longer see microwaves on the roofs of all the big buildings in your city or on hilltops? Why? Because we have fiber optics, and by using light in the fiber optics, we have enormous beam width, which makes possible a high-speed internet, and it makes possible the high-definition television. Well, exactly the same benefits result here. You can think of the focused channel as the fiber connecting you to it and vice versa. The other surprising thing is that the star noise problem goes away the further away you can do this, because at position A, you're focusing the laser from here to this 21 light minute diameter circle. The receiver is in here on a planet or near one, and the star is in the field of view right there. If you come out here further away to B, now you have the same illumination here. The same amount of power arrives in this circle and also in this circle, but the star is getting weaker and weaker as the inverse square of the distance, and so the further you go, the better the signal to noise gets. The required laser power versus the range in light years to give a signal to noise of 100 in a bandwidth of 10 gigahertz, it reduces to this. The laser power is equal to this number 4.8 times 10 to the 12th over n squared, which is the range in light years. And as an example, 1 megawatt of laser power from a 100-meter transmitter is detectable from 5,000 light years with a 4-meter telescope. So quite reachable from where we are now. We looked in the old paper at various ways of doing this. This is a huge solar array powering 3-electron laser here. You have a whole bunch of these beam directors that are aimed off to the stars, and you're kind of time sharing the laser to do that. What's a lot more fun is to think ahead a few centuries where we can put von Neumann machines, say on Mercury, or they can do the same thing around some planet conveniently located near their star with no atmosphere. And what it does is take the silicates and convert them into, first of all, solar power cells and photoreceptors, sensitive photoreceptors and light-emitting diodes, and you make an interstitial phased array that covers the entire dark side of the planet. And on the light side is your solar power, so that, for example, on Mercury, the side facing the sun receives all the time about 10 to the 14th kilowatts. And right now, light-emitting lasers, solid-state lasers exist that are putting out about 100 watts per square centimeter. And so they're getting better and better. The light's kind of trashy now, but we'll know how to phase up. So this array of sensors would be looking at all of the galaxy. It would be adjusting the size of the photo cells receiving the light, so it sees each star and it says, aha, I know that's a type G star, and so it must have a life zone the size we're interested in. And so it then adjusts the size of the patch of light-emitting diodes, lasers, so that they illuminate that. So right back where it sees it, of course, it can put in corrections for the position of the stars, changing all of that, tracking them, you accumulate the data. Okay, now I want to shift gears again and talk about the state of technology now. How much time do I have left?
We've got about 3 minutes before Q&A.
Oh dear.
Well, about 8 minutes, I guess.
8 minutes?
Yeah.
Okay. In order to have a telescope, there's a thing called the Strel ratio. The reason they're still grinding glass after 150 years is that you need something that's pretty smooth and has small errors in it. In fact, this is the error, a tenth of a wavelength, delta lambda over lambda, and 1 wavelength. And the point is, you go from 100% perfect optics, you fall off a cliff when the error in the surface gets more than a tenth of a wave. Adaptive optics technologies were identified nearly 40 years ago as the way to cure this. A lot of things, including the Keck telescope now in the infrared, use deformable mirrors where you've got a bunch of little piezoelectric devices to bend a glass membrane and improve the seeing of the system. I got interested in the late 80s in generalizing that idea to what I named Pamela, phased array mirror extendable large aperture. The basic idea here is you mass produce these smart little machines that have edge sensors and actuators. You cluster them together like this, and you can populate a very, very large surface that way. We got from DARPA and NASA $9 million bucks over the years and built the test apparatus for this at Marshall Space Flight Center. And this was the proof of principle telescope. It had 36 of these segments, first, second, third generation. And now I'm pushing the fourth generation. I realized that what we needed to do was just use silicon wafers, which are really lightweight, and Kevlar background, and think of each of these as a hexagon with a real smart thing. We've got 2 new patents on how to do this, make the segments. You can use these things on big, cheap telescopes. You can build a telescope like a radio telescope, and it wants more than anything else to be a perfect optical telescope. And so you can couple it to a free electron laser and use it to beam energy from a big aperture. We even made a nice model of that to show how it could be done. But when we started thinking about putting it in space, we came up with a different idea that we named MIC, which is magnetically inflated cable. How do we make very lightweight, very large, rigid structures? Ampere told us how to do it in 1835. You flow current around the loop like this, and since the magnetic fields and the current oppose each other on each side, it bulges out and forms a circle like that. And so what you do is use the new high temperature superconductors that superconduct around liquid nitrogen temperatures are better, with super insulation on them in space. You start a current flowing in them, they bulge out and form nice perfect circles. And so we have 4 of those in this box here with Kevlar cables coupled across, and as it unfurls and does this, it drags out the membrane mirror, which can then be covered with the Pamela segments to make a huge telescope. And by the way, if you want to make a light sail, that's a lot easier because the surface doesn't have to be perfect. If you want to capture an asteroid, you just make it a concentrator, focus energy on the asteroid, and evaporate the surface, and you can steer it where you want. In fact, if you want to go to Mars, you capture a little 10 or 20 meter diameter asteroid. Your machines burrow inside and make a nice Hilton hotel room in there, and you get inside. It's touching the orbit of the Earth at one side, the orbit of Mars. You travel for 8 months and are protected from cosmic rays while you play computer games. If you do all of this, what you find is that you can build a telescope in space. If we build the Ares 5 payload, 65,000 kilograms could be landed on the moon or in lunar orbit. Then the largest deployable MIC Pamela telescope would be 332 meters in diameter, which would give you prodigious capabilities for imaging planets around other stars, doing spectroscopy on their atmospheres, and hey, by the way, looking for serendipitous laser communication among them, or sending laser beams to them, and so on. Pamela and Nick have many advantages: much lower cost telescopes, ultra lightweight systems, long throw actuators that correct the structure and the optical pointing errors. You control the pointing by just controlling the phase of the light. You don't try to do it by steering the device itself. And at the same time, it solves all the thermal problems because you've got a big enough reflector that that and the secondary optics can be big too, and so you don't fry the optics with the lasers in the process. Okay, that's the presentation.
Okay, we got 5 minutes.
On behalf of my co-authors and myself, I'd like to say it's such a pleasure to meet someone who's crazier than we are.
I knew it. I know I'm in good company too. Yeah.
A few years ago, I did a little paper at Acta Astronautica with a student who really turned out to be a true webmaster. I had her go through the 5,000 or 7,000 known NEOs to actually try to pinpoint a few that would allow you to do Earth to Mars, Mars to Earth, or in one case, Earth to Vesta transfers. And they're out there.
Oh, they're
They do
definitely
this.
out there. And more than that, what's really fun is that these near-Earth objects, a lot of them have very low relative velocities with respect to the Earth, 3, 5, 6 kilometers per second. So if we can build up a catalog of them and know when a nice choice one is coming and get out there and wait for it so that our concentrator can start working on it. I've published a paper on this, by the way. Then it's possible you fry off about 30% of the mass, which is like a rocket engine, and steer it into a trapped orbit at the L4 and L5 position on the lunar orbit. And then you can engineer it any way you want. Take it somewhere else after you've got it right. Any other questions?
Very good, thank you.